missed a little bit of this anyways. Okay, so today we're starting the chapter now on continuity and homeomorphisms. So let's quickly get intuition for what each of those things is, or briefly remind us from using high-level language what a topology gives us. A topology essentially gives us a minimum structure we need on a set to talk about proximity, to talk about points in some sense being close to each other, next to each other. And so we already talked a couple classes ago about taking a limit. That's points getting closer and closer to a point. So a topology is a minimum structure that we need to start talking about proximity between points. Intuitively, using high-level language, continuous functions are functions from one topology to another topology that preserve proximity. It preserves that structure. So if 2 points were close to each other in one topological space, and I run them through a continuous function, when they come out the other side, they're still going to be close to each other. And if 2 points were far from each other in one topology, when I run them through a continuous function, they're still going to be far from each other. So, high-level language, continuous functions preserve proximity. And we're coming close now to give you a brief peek into what we'll talk about next time, homeomorphisms. A homeomorphism is a function that's a bijection, so 1 to 1 and on 2, that's continuous, and its inverse is continuous. So it's continuous both ways. So if I go from one set to another set, it does so in a continuous way, and if I go back through the function, it does so in a continuous way. And so if I get a function that's a bijection, that's continuous, and its inverse is also continuous, then we call that a homeomorphism. And what it means is those two topologies are homeomorphic. They're somehow the same. Homeomorphic for topology is kind of like congruence for geometry. The same way that when we said two geometric figures are congruent, that means they have all the same geometric properties. When we say that two topologies are homeomorphic, that means that they're going to have all the same topological properties. The only topological property we've talked about so far is Hausdorff, whether a topology is Hausdorff or not, so that's the only property we have so far. But these homeomorphisms are going to be those things that preserve structure for us, that in some sense say things are the same. And they're all based in the fact that they're continuous one way and the next. So continuous functions preserve structure one way, and then if it's homeomorphic, it preserves structure both ways. So it says they're somehow equivalent. Okay, so that's high level where we're going. Today we're just going to talk about continuous functions, these functions that preserve proximity from one topological space to another. There's the one that's hopefully not dead. Okay, and so before we get into this, we're going to play kind of a weird game. And I'm going to try and get you used to what we mean by continuity in calculus. So first we're going to get you used to what continuous means in calculus. We're going to give you the full-fledged, here it is, Epsilon-Delta definition of continuity in calculus, the thing that terrifies calculus students. It's much harder to understand than what it just means for a function to be continuous in a topology. The reason that I'm going to walk you through this much more difficult definition, the one that's hard to understand, is because it comes with a much prettier and more intuitive picture. So this one, it makes sense. Oh, that's why it's continuous. Whereas when I give you our definition of continuity, you're going to say, how is that even related? And it's going to take a lot for us to get to the proof that finally says, look, these are the same. So the calculus definition of continuity is just going to be a special case of our general definition of continuity. Here's our general definition of continuity. It's much prettier than the calculus one. So we're going to work up to the calculus one. We're going to do that by starting out playing a game here. Here's our game. Well, let me say one more thing for you. Just basic intuition going back to your grade school notion of functions. What is a continuous function? It's a function that I can draw without picking up my pencil. This one is continuous. This one here is not, because I have to pick up my pencil to jump and draw it. So that's like the most basic intuition for what a continuous function is. Okay, so now we're going to play a game. Here's the game we're going to play. We're looking at this function, f of x is equal to 2x plus 1. And we're going to focus in on the point 2 here, and f of 2 that comes out. We're going to think about this function as mapping this real number line to this real number line. And so it sends this point 2 up and over to this point 5. So we're going to think about it's mapping all these points onto these points and kind of stretching it out and shifting as it goes. That's how we're going to think about this. Now, here's the game that we are going to play. I am going to pick random numbers over here. Well, first off, let's get intuition really quick for what we mean by absolute value. So here's what we're going to be playing a game. Here's what our game's going to do. I'm going to be placing intervals around f of 2, and your job is going to end up with intervals around 2 that map into the interval I give you. A little bit dense, but once we get playing, I think you'll understand it. One more thing to get intuition for what I have written here. Intuitively, how do we think about the absolute value of x minus 2 being less than a number? If I say the absolute value of x minus 2 is less than 1, intuitively, what does that say? It says that the distance between x and 2 is less than 1. That's what it means for the absolute value of x minus 2 to be less than 1. Remember, absolute value of a difference gives you kind of a one-dimensional distance. What's the distance between the number 3 and negative 7? 10. How do you do that? 3 minus negative 7, take its absolute value. Or you could have done negative 7 minus 3, take its absolute value. Doesn't matter which way you do it. The distance is 10. So we're picking numbers here. So if I tell you that the absolute value of x minus 2 is less than 1, then our numbers here that we are plugging in for x are between 1 and 3. They're the numbers whose distance from 2 is less than 1. So here's a number that satisfies it. Here is. This definitely does not. 4 is not within a distance of 1 of the number 2. Similar over here. Notice that f of x minus f of 2 being less than some number means that our distance from f of 2 is less than some number for our output. You with me? So I'm going to be coming up with numbers here. You're going to try and come up with the corresponding number here that makes it true. I'll do the first one, and then I'll let you guys try a couple. So let's say that someone over here said, I want this to be less than 3. So, well, that's a bit big for my drawing. Let's pretend that they put a 2 there. So less than 2. So they're saying, I want you to bound an interval around 2 such that when you map it, all the points are within 2 of f of 2. All the outputs are within 2 of f of 2. So all the outputs have to go from here to here. Can't go down more than that, can't go up more than that. So I want an interval of inputs whose outputs don't go past it. And notice that our interval is just the interval from 1 to 3, not including 1, not including 3.
Why don't you include 1 and 3? Oh, because it's less than.
Because we want less than 2.
Yeah.
Run 1 through the function. If I run 1 through the function, 2 times 1 is?
1.
2 times 1 is 2, plus 1 is 3. Is 3 within 2 of 5? Remember, f of 2 is just 5. There's a reason I'm writing it as f of 2 there rather than 5. No, so we don't include the 3. Okay. But we do include, what would it be? 5 halves, 2 and a half, 5 halves. We do include that. So these are all the numbers, and so our distance here is 1. As long as you pick an x who's within 1 of 2, then your image, the image of that point, if you pick an x, so an x might be right there, so the x comes up, then f of x is here. There's f of x. As long as the x you choose is within 1 of 2, then the f of x that comes out will be within 2 of f of 2. You with me? All right, now I'm going to make my interval a bit smaller. So what if I bounded it to 1? Then what does the number over here have to be? So you can't go past here, and you can't go past here. How close to 2 down here do we have to be if our output is going to be within 1 of f of 2?
One half of 2?
Just 1/2, right? So if this is 1/2, then this will be less than 1.
Right.
Let's plug that through really quick. What's the point furthest this way we could take but not quite get?
With 1/2, it's 1/1/2.
It would be 1 1/2 or 3/2. So you're saying it's the interval of 3/2 to 5/2, right?
Yes.
All the points within 1/2 of 2. Okay, so when we run 3/2 through this function, what do we get? 2 times 3/2 is
6/2.
6/2, which is 3, plus 1 is 4. So 4 is barely not within 1 of 5, so good. So we get close to 4, but we don't quite get 4. When we run this through the function, what do we get?
5/2.
6, right?
Oh,
10/2 plus 1.
yeah.
So we get 6. So we get the numbers from 4 to 6. When we run this interval through the function, we get out this interval. And notice that those are all the points within 1 of 5. Let's play it again. Okay, so you did it when I did 1. Let me pick a smaller number. What if I choose 1/2? Then what's your number over here going to be?
1/4.
1/4. Right? Because all this function is really doing is whatever you do it, it's going to double it. It shifts it, but it just doubles whatever you're doing.
Yeah. Okay.
And so if you're within 1/4 of 2, the output is always going to be within double that of f of 2. And notice that for any number I choose here, now you have a formula. For any epsilon I choose, you know how to find a delta such that this is true. And the delta that you would choose is delta, we always choose it just to be epsilon halves. So for any epsilon I come up with, you were always able to find a delta that made this implication true. And that's the game. That's the game you play in your head, is you need to, if you're going to show a function is continuous at a point, then you need to show that for any epsilon I give you, you can always find a delta that makes it true. When I chose 2, you chose 1. When I chose 1, you chose 1/2. When I chose 1/2, you chose 1/4. No matter how small I make that epsilon, you can always find a small enough delta that makes this whole thing true. If I make my epsilon smaller, you have to make your delta smaller. But who cares? You can always make it smaller. Now let's play a version of the game where you can't win. So we're going to where it's possible for you to not win. So we're playing the game again over here. Different function this time. So f of x is a function x plus 1 when x is greater than or equal to 1. And it's just x when x is less than 1. So f of 1 is, let's see, f of 1 is, when we plug in 1, let's see, is 1 greater than or equal to 1?
Yes.
So we use this top function. So f of 1 is 2. So f of 1 is 2. F of 2 is, 2 is greater than or equal to 1, so 2 plus 1 is 3. So f of 2 is up here at 3. F of 0 is 0 greater than or equal to 1?
No.
No, it's less than 1, so we use this one. F of 0 is just 0. So that's graphing out the function. Now you see that this function doesn't behave very well at this point. It's not continuous. Which means that when we try to play this game at this point, I'm eventually going to be able to win. Let me start out by not winning, and then I'm going to start winning. Okay, let's say that I pick, I want you to keep us within 2. So within 2 of f of 1. So we can go up to here and down to here. What is your interval around 1 going to be, so that when we map all those points, we get within my interval? Can't really see it that well, can you, with the blue? So here's, I'm saying we're within 2 of f of 1, so from here to here. So what interval can I place around 1 so that when we map all the points, we're for sure in there? You don't need to think through a formula, just give me a number by looking at the picture.
2.
2? Within 2 points of 1? If you put in 2 here, so all the x's that are within 2 of 1 would be all the x values from here to here. Notice where the output of these x values go. They go clear down here. I'm saying you have to keep the output in this range. Your point here has an output down here. So you need to find a number such that all your outputs are going to be greater than 0, but less than 4. So you need to give me a number here so that the function, as long as we pick values less than the number you choose here, then all our outputs are within the range 0 to 4. So what interval could you place around 1 so that all your outputs are within 0 and 4?
0 to 3. What's that interval? 0 to 3, round 1.
You could do the interval 0 to 3. The interval 0 to 3. So you could definitely do the interval 0 to 2. You don't need to find the biggest interval, you just need to find an interval.
Yeah. So,
And maybe we're wondering, at the 0, didn't quite get it. So let's just keep our life simple. For sure it works at a half. If I limit myself to a half, then all those points, when we map them up, their outputs come out right here, which is inside the orange interval I drew. So 1/2 works.
yeah.
Okay, now what if I would have chosen 1/2 here? So if I choose 1/2 here, so now you're trying to get within, kind of making a mess of my picture here. So now you are trying to get in within 1/2 of f of 1. So you're trying to pick some interval around 1. Let's just redraw that. So you're trying to pick some interval around 1 such that its image is always within 1/2 of f of 1.
That doesn't work though.
It doesn't work. We can pick over here 1 over 10,000 there. So that is just such a teeny interval, it's stupid to even try and draw it. But all these points over here come up just a little bit left of that hole. And so their output comes up right around here, which is outside my orange interval. There is no interval you can place around 1 that keeps you entirely in my orange interval. So this function is not continuous at 1, according to our Epsilon-Delta definition. So we just played the game a couple times. Now I'm going to give you the full definition. You can see it's not that bad. What does our full definition say? So f as a function from the real numbers to the real numbers. Notice that's what we were doing here. We were mapping r to r. F from the real numbers to the real numbers is continuous at some point x0 in r. If and only if, for every epsilon I choose, this was the epsilon number over here. If and only if for every epsilon number I choose, you can find some delta such that if x is within delta of x0, the point we're saying, is it continuous at this point? Over here our x0 was 2, over here our x0 was 1. Okay, so it's continuous at the point that we're talking about. Here we were wondering, is it continuous at 2? The answer was yes. Here we were wondering, is it continuous at 1? The answer was no. So our function is continuous at some point x0 in r, if and only if, for every epsilon I choose, you can find some delta such that if x is within delta of x0, then f of x is for sure within epsilon of f of x0. If that is the case, then the function is continuous at that point. So it was the case here. It was true that for any epsilon I chose, you could always find some delta that satisfied that implication. So if for any epsilon you can find a delta that satisfies this implication, then it's continuous at that point. If I can come up with even one epsilon where you cannot satisfy it, then it's not continuous at that point. It has to work for every epsilon. So over here we found an epsilon, namely 1/2, such that no matter what delta you chose here, you can never satisfy the implication. And intuitively, what was happening? I told you that continuity preserves proximity. Notice that on the real number line, this number 1 and this number right next to 1 are close. But when we map them, one got mapped clear up here, and this number close to 1 got mapped clear down here. Those are no longer close. So when we mapped these to these, we did not preserve proximity. Points that were close here before we mapped them were not close here after we mapped them. That's why I'm saying think about the function as mapping these points to these points rather than think about it as this actual line. So that's the topological way of thinking about it. Proximity got broken. The calculus way of thinking about it is I had to pick up my pencil. Okay. So there's the definition. I think you guys kind of got with the game, but let me walk through the definition one more time for what it means to be continuous. So what it means to be continuous is, what it means for function, here's some function to be continuous at a point x naught. It means that for any epsilon I choose around here, for any interval I choose around here, so this top point would be f of x naught plus epsilon, and this bottom point here would be f of x naught minus epsilon. So this is just our interval, all the points within epsilon of f of x naught, right? So if for any epsilon interval I choose around here, you can always find some interval, doesn't matter how small, you don't have to get the whole thing. You just gotta make it small enough that the whole thing fits inside of there. If you can find some little teeny interval, so that point right there would be x naught plus delta, and this little point right here would be x naught minus delta. If you can find some interval, you move that one over a little, x naught minus delta. It's not delta, that is 6. Although I'm writing so small, it doesn't matter. Such that when we map this interval through, so when I map this, it goes over to, shouldn't have written those numbers. It goes over to there. When I map this, it goes over to there, and yes, we did it. This whole interval's image is inside this thing's interval. So I can do that for any, if I make the epsilon here smaller and smaller around that point, you can just make that smaller and smaller, and keep it completely contained inside. The broken picture here, if I pick a small enough epsilon, notice I don't pick epsilon like this, or you'd be able to do it. You can find some interval that always stays within this, but if I pick a sufficiently small epsilon here, so I pick a small enough epsilon like this. Now, it doesn't matter how teeny tiny you make this delta. Doesn't matter how teeny tiny you make it, because these points right here are going to map over to here, whereas these points right here get mapped up to here. And so that's the whole interval that comes out. But the point is, well, we don't get the whole interval. We get a chunk there and then a little bit here. But the point is we get points that map outside the interval. And so it's not continuous at that point, according to the Epsilon-Delta definition. Okay, that's a lot to swallow. In the calculus class, you would spend a whole lecture walking you through that definition, lots of examples, getting you really comfortable with it. But this is the calculus class.
It's pretty new for me just seeing the absolute value less than method for creating
A distance?
an envelope between some point. That's just like something I get my head wrapped around.
All right, well, hopefully this definition at least appeals to your intuition.
It does.
That's good. Okay, so now what do we mean when we say a whole function is continuous? A function is continuous if it's continuous at every point in its domain. So this function we would say is not continuous because there's a point that broke continuity.
Isn't that?
This function is continuous at this point, it is continuous at this point, it is continuous at this point, it's continuous at every point except that one point. That's the only point where it's not continuous.
Isn't that definition included in definition 4.1? So a function is continuous if and only if.
This is saying it's continuous at a point. This is saying it's the whole function's continuous. That's what I'm saying. So this function, even though it's not continuous at this point, it is continuous at this point over here. So this function is continuous at almost every single point. There's only one exception. And so even though it satisfies this definition at infinitely many points, since there's one point that doesn't satisfy this definition, we say that the whole function is not continuous. So this function is continuous, this function is not continuous. So don't accidentally get those mixed up in your head. A function can be continuous at a point, but still not be a continuous function.
Okay. Makes sense.
Okay. Now, let's get into the topological version of continuity. So, let X be a topological space, and Y be a topological space, and let F be a function from X to Y. Then F is continuous, if and only if, for every open set in Y, its preimage is open in X. if and only if for every set that's open in Y, its preimage is open in X. If V is an open set in Y, run it backwards through the function, find its preimage, then its preimage is open in X.
Yeah, okay, that makes sense.
This is very close to how we define quotient maps.
That makes total sense.
The way that everyone says this is, what does it mean for functions to be continuous? Everyone says the preimage of open sets are open. So that's the mnemonic sentence we use to remember what it means for functions to be continuous in topology. It means the preimage of open sets are open. If V is open in Y, then its preimage is open in X. The preimage of open sets are open sets. The preimage of open sets are open. That's the way that anyone would say it on the fly. So that's what it means for a function to be continuous. What does that have to do with this notion that we have up here of you can't pick up your pencil when you're drawing? Yeah, it's in no way intuitive that this is equivalent to this when we limit ourselves to standard topology on the real numbers. But it is, and we'll get there. So let's get a picture of this, that definition in action to understand it. What does it mean for f to be continuous? It means come over here, so maybe set this up. Here's x, and it's got its topology. Here's y, and it has its own topology. Two completely unrelated sets. F is a function that maps x to y. Come over here in y, and pick some random thing out of tau sub y. Pick some open set, call it v. Here's some random open set in y. Look at its preimage. Here's its preimage. If its preimage is open in x, then the function is continuous. If for every open set I find in y, its preimage is open in x, the function is continuous. If I can find even one set over here that's open, and when I run it backwards through the function, its preimage isn't open, then the function is not continuous. It has to be the case that for every possible open set over here, when you find its preimage, it's still open over here. Okay. Reminder, some things that we're going to be using. We already talked about these when we did quotient maps, but good to remind you about these again. If I take, so A and B are sets here. The preimage of A intersected with the preimage of B is just a preimage of A intersect B. And the preimage of A union the preimage of B is equal to the preimage of A union B. And another one we're going to use, right over here, we're also going to use the fact that the preimage of A minus B is equal to the preimage of A minus the preimage of B. So these are things going all the way back to, I can't remember what chapter, preliminary stuff, that's clear back in chapter 0, theorems. But notice that we're going to be talking a lot about preimage stuff, and so these three facts are going to be quite useful in talking about continuous functions. Because over and over again, what are we going to do? We're going to take an open set and look at its preimage. And so these are going to be some useful things to remind us of, or to keep in mind. Okay, so that's a big mouthful of a definition. A lot of high-level stuff. Let's get down into the nitty-gritty now. Let's take a concrete topological space, a concrete function, and let's look at it. Is it continuous or not? So we're going to use x is a set A, B, C, D. Y is a set 1, 2, 3. Here's f. F is a function from x to y. It maps everything in x to something in y. It maps A to 1, B to 1, C to 2, D to 2. Notice that we don't have to use up all of y. Okay. Question. Is f continuous? So far, that's a dumb question, because I didn't tell you the topology on this and on this. Continuity makes no sense without topologies, because a continuous function is a function that preserves proximity, and proximity doesn't make sense without topology. So I've drawn out a picture of what our topology is. So without this picture, it makes zero sense for me to ask you, is this function continuous? You're used to being asked, is a function continuous in your algebra courses, but that's because it was always understood we're talking about on the standard topology on the real numbers. And so you already had that topology and you're real comfortable working with it so much that you don't even think about it.
Yeah, okay, makes sense.
It's always good to remind you. I already said this once, but maybe we're saying again. One of my teachers, to help me get intuition for the difference between the real numbers and the set of the real numbers. The real numbers, I'm used to thinking about them, and what the set of real numbers actually is. He says, take the set of real numbers, that real number line, draw them all out. Now rip it all to shreds, that whole real number line, put it in a blender, blend it up, and then dump it in my hand. He says that's the real numbers. There's no structure. There's no this real number is next to this real number. Not when we're just talking about the set of real numbers. It's just a set of things. And so it's that topological structure that we give it that then makes it make sense to talk about continuity. So, F is a continuous with this topological structure. And you remember how these pictures work, what I'm saying? So I'm saying over here, so X is a set A, B, C, D. Y is a set 1, 2, 3. I'm saying the open sets over here are the set AB, the set ABC, the set C by itself, the set C and D, and then the whole thing. And similarly over here. Is there anyone confused by the picture? Make sense what I'm calling open set and why I'm not? Okay, so then let's just test. Is F a continuous function? So I'm wondering, is F continuous? How do I check?
This pre-image is open.
If its pre-image of open sets are open.
Yes.
So which open sets am I taking the pre-image? So I'm looking at the pre-image of open sets. Which open sets am I looking at? The ones over here or the ones over here?
Y.
The ones in Y. Because we're looking at their pre-image. My function maps this way, so pre-image is going that way. So I need to check every open set over here, find its pre-image, and make sure it's still an open set. So, one open set we have over here is the set just containing 1. Right? What's the pre-image of the set containing 1?
A.
You have to look at your function to know. So what's the pre-image of 1?
A and B.
A and B, the set containing A and B. These are all the points that map to 1.
Yeah.
Notice that this function does not need to be 1 to 1, and it does not need to be on 2 in order to be continuous.
Yeah.
And that function is neither of those things.
Yeah.
So the pre-image of 1 is AB. Is AB continuous?
It's open.
Or open, thank you. Is AB open? Yes. So far, F is looking good. Let's try the next one. So we checked that open set. Now let's check the open set containing 2. Is the pre-image of this still open?
Yes.
What's the pre-image of 2?
C. Set containing C.
C and D, right?
Yes. Sorry.
Is C and D an open set?
Yes.
We have that circle representing C and D together. So C together with D is an open set in X. We took an open set in Y, looked at its pre-image under F, and we got an open set in X. Let's try the next one. What haven't we tried yet?
1, 2, 3.
We haven't tried 1, 2, 3 yet, but we also haven't tried just 1, 2. Let's try that really quick. Just 1, 2 is open in Y. So let's look at its pre-image under F. And what's its pre-image? What's that?
A, B, C, D.
A, B, C, D. It's all of X. Is all of X open in X?
Yes.
Wonderful. And then finally, let's look at the pre-image of all of Y.
No.
It doesn't work because 3 doesn't have anything, right?
Right.
No, the pre-image of 3 is just the empty set. We're still fine. So it's still just X.
Okay. Yep. Forgot about that.
So there's no problem with us getting points over here and asking for their pre-image, even if nothing mapped to it. Perfectly fine.
Of course. Right.
Okay, so that was for F. Now we're going to ask the same question. Notice that we can have tons of functions from X to Y. F was just one possibility. Let's look at another possibility, G. And notice that we still plug in all the same sets because these are all the open sets on Y. And so we need to check all their pre-images under G. Where's my eraser? So, what is the pre-image of 1 under G?
A.
Just a set containing A. Is that an open set?
No.
No. A by itself is not open. So already this function is not continuous. But just for the sake of getting comfortable calculating these pre-image things, let's keep calculating pre-images. But we already know G is not continuous because one set is enough to break it. It did not preserve proximity. Okay, what's the pre-image of 2? B and C together, both map to 2. Is BC an open set?
No.
No. So we broke it again. What's the preimage of 1, 2?
Set containing A and B.
The set containing A and B.
And C.
And C.
Oh, oops. Can't read the names.
If this is the preimage of 1 and this is the preimage of 2, then the preimage of 1 and 2 has to be the union of those two things.
Oh, yeah. Didn't think of that.
Okay, and then the preimage of all of Y,
All of it. X.
did all of X map into it?
Yes.
Yeah. All of X always and forever has to map into it. Because a function has to map, if F is a function, or G is a function from X to Y, it always and forever has to map all of X to something in Y. So the preimage of Y always and forever has to be X. We had to map all of X to something in Y. Okay, so that was G. Now let's do H. And see if H is a continuous function. So what's the preimage of 1 under H?
C.
Just C. Is C by itself open in X?
Yes.
Yes. So far we're good. What's the preimage of 2 under H?
Set containing A and B.
A and B. Is the set containing A and B open in Y?
Open X then.
Or open in X, thank you. So we're good. What's the preimage of 1, 2?
Set containing A, B, C.
A, B, C. Is that open?
Yes.
It better be.
Yeah.
Because if this is open in X and this is open in X, their union better be open in X or we didn't write topology over here.
Yeah, right.
Maybe we should have started with that. Are these things topologies?
Yeah, I don't like that.
They are topologies. I happen to give them to you, but should have started with that. Maybe left one out and then made you think about it. Could have gotten rid of the one just containing C. That would have been a good question. All right. And then finally, what's the preimage of Y?
X.
X. You don't even have to think about it. That's always and forever the case.
Right, yep.
This is going to sound ridiculous because it seems like I should have already understood this. I guess my first question is there a way to describe how using the definition of continuity, the topology definition, how could you just explain how that, how figure 2 up there is not continuous using that definition?
How can I use this definition to show that this figure is not a continuous figure?
Yeah.
Intuitively, here's how it works. What are our open sets when we're on the standard topology on the real numbers?
All real numbers.
What are our
The intervals.
All the intervals.
the intervals?
Yeah.
Intervals are our open sets on the real numbers. So, look at this. I'm gonna quickly redraw a picture here. Just get rid of the ugliness that we have, and show you how it doesn't work. Our function. So I've got some function. It comes down like this. So some function like that, right? Now, here's our f of x naught. Here's our x naught. A function is continuous if the preimage of every open set is open. Right? So let's look at an open set containing f of x naught. Here is an open set. That interval right there contains f of x naught. Let's look at its preimage. Run backwards through the function. If we run backwards through the function, notice that those points are missed.
Yeah.
Okay, so when we run it backwards and we map down, then we're going to get this maps exactly to here, including this point. So maybe dark line for including. but not including this point.
So that makes it closed.
So if we zoom in on that interval, here's x naught. Here's where that orange line is coming down. We're zoomed in now. It is all the points from here, not including that, to here, including that. So it's open on this end, closed on that end. That is not open in the standard topology. So the preimage of this set was not an open set. And it's only continuous if the preimage of every open set is an open set. So if I can find one counterexample, then it's not continuous.
That's so, I mean, I believe it. It's amazing that that applies in all circumstances. But
It took a lot of time to develop this topology field. Calculus was developed way before topology. And so it was a ton of work trying to get at the root of what these concepts are exactly. One of the major reasons why we do all this is because we don't want to be stuck just doing calculus on the real numbers. For example, the torus, that donut shape, the surface of that donut shape. I want to be able to do calculus on that. I want to talk about calculating derivatives, calculating integrals, calculating areas. I want to be able to do all that on the torus. I want to be able to do that on any, we think about them as manifolds. Any manifold shape you give me, any nice closed surface, I want to be able to do calculus on that thing. And getting at the root of topology is a lot of what we had to do to get down to what exactly this concept is. What is the minimum structure we need, and then make sure that when we create our abstractions for these things, we include that minimum structure.
Okay.
So there is nothing, it is amazing. There's nothing intuitive about this somehow gives you this.
Yeah. Yeah, that's so interesting. Okay, so now my ridiculous question.
Okay?
I know what an open set is, and technically, as far as I can tell, it's just a set.
It's just a member of the topology that follows some rules.
Yeah, so okay. So I understand my intuition of an open and closed set on the real numbers, you know.
Just open intervals and closed intervals,
Yeah,
basically.
like I understand those in the more of the mapping visual context. What I don't understand is what the heck is an open and closed set within just a set? How do I know?
In just these weird discrete sets.
Yeah, but how can I look at a set and say it's a closed set?
Is its complement open?
Okay. How do I? Frick. Oh, you're right. That makes sense.
Right, and there's not going to be any intuitional, oh, that makes sense, that this function is continuous from here to here. There's no reason that appeals to your intuition. Oh yes, I can draw that without lifting up my pencil.
Yeah.
No, you don't get any of that intuition. So that starter intuition for what we had, for what continuity is, it turns out it's a much deeper concept than that. And that there are ways to capture continuity without having the nice, oh, don't pick up your pencil.
Okay. So in a closed set, which is essentially where we go straight to the
An example of a closed set is the set containing D over here. Set containing D is closed. Because its complement is ABC, which is one of the open sets.
Okay, I'm talking about let's go back to the rep.
Back to where things feel good.
Yeah. Let's say we have a closed set.
So that's going to be a closed interval or unions of closed intervals.
Yeah.
Okay.
How can I prove that a closed set, its complement is open?
Yeah, that's by definition.
That's exactly how you do it.
I know, but I know that I'm saying if something. Okay.
Pictorially, here's the way that you know it. So how do I know that some closed interval A to B is in fact closed?
Yeah. Well.
Intuitively, how do I know that? Look at the complement of this thing. The complement of that thing is negative infinity to A, not including A, union together with B to infinity, not including B. Open interval. So union of open intervals is open. This is everything that's not those points. So those points must be a closed set.
Well,
So we define our open sets, and then how do you know if a set is closed? You simply look at its complement
no.
and ask, is it open?
I understand that part. I don't understand why we decided that the intervals are what made it closed, like the integer.
The integer.
Okay.
It just so happens that these closed sets are closed. I mean, we set up topology. Remember, it's working backwards. We had this structure. We were doing calculus, and we were working with the standard topology on the real numbers long before we were calling it that, long before we had a concept of a topology. And so we were saying, what exactly is it that we're doing on the real numbers? And is there some way we can abstract that so that we can start doing it on different sets that aren't the real numbers? And so when it was all said and done, everything was configured so that open intervals on the real numbers would still be open sets. So when we create topology, open intervals better have still been open sets. Closed intervals still have better been closed sets. So we got used to this topology that we want on the real numbers. And we said, these concepts that we're working with on the real numbers, is there a more abstract notion of them that we can then apply to things that aren't the real numbers? So we were working backwards from it.
Right. So what I'm just, okay, take for instance, in the figure, the second figure, we concluded that because there was a point,
That endpoint included?
yeah, that point, that is what made it not open.
Right. By definition, open sets in the standard topology are open intervals and unions of open intervals. That is not an open interval, and it's not a union of open intervals.
Well, okay. So how can I convert that to a set, and then I can look at the set and say, oh, this is a closed set.
If it ever looks like this, it's a closed set.
I'm talking, yeah, well, okay, how do we take that concept and put it into a set? And I could say, oh yeah, that's a closed set.
This is the set. It's not a concept, it's the set. A more concrete set. So I give you something like pi to 297.6 plus the square root of 2. Included. That's from a number to a number in a closed interval. It's a closed set. Its complement is going to be open. If I look at all the points that aren't those points, I may have unions of open intervals. This is all the numbers from pi to 297.6 plus the square root of 2, whatever that is. It's all the numbers from this number to this number, including the endpoints.
Okay, so why does including the endpoints all of a sudden make it closed? That's what's confusing to me.
Because when we take its complement, when we take the complement, things like that, we get things that are open intervals. And by definition, the standard topology on the real numbers is union of open intervals. It's how we defined the topology on the real numbers. There were other topologies we talked about on the real numbers, the finite complement topology. In that topology, this won't be closed. We talked about the lower limit topology, the upper limit topology.
I know we went all through that, and now I'm just like realizing I don't understand it as much as I thought I would.
The feeling you always get at the end of one of these classes is, okay, now I'm ready to take the class.
Yeah, for sure.
That is a common feeling. Because it's a lot. And then the second time you're taking the class, you're realizing, oh, we're setting up for this. Oh, we're setting up for that. Oh, this is coming back for this. And so someone who's taken it before, when we first come over these things, way back in the preliminary stuff, they're paying close attention because they know that we're going to be doing a lot of inverse mapping.
Yeah, for sure.
So, yeah, it's hard to just get the intuition for it. It's one of the most unintuitive fields of study there is, topology. You don't get nice pictures like you do in calculus.
Okay, let's keep running it.
Well, feel free to ask whatever questions.
Yeah.
Just try to help as much as I can. It's not like we're against the clock here. I don't know. Probably should. No, we should. We're good. So we just finished up this example. Were there any more questions on this example? Okay. So now we're moving on to our next example. We're looking at the identity function from x to x by, what does the identity function do? It maps x to x. It maps everything to itself. You've used this function 100 times. If we're talking about the identity function on the real numbers, f from r to r by f of x is just equal to x. Maps everything to itself. Maps 1 to 1, 2 to 2, 3 to 3. The identity function. Now, anytime it's understood that that has a topology and that has a topology, if we're ever talking about continuity. So example, I'm going to show you that this function is continuous. That's what we're saying. So, really quick, going to argue that the identity function is in fact a continuous function. How do I prove that a function is continuous? So, one, let identity from x to x by identity on x is equal to x. How do I prove that a function is continuous?
If the output's preimage is an open set.
Yeah, if the preimage of open sets here are open sets here. So 2, let u be open in x, in this x.
Are you going to label the x's?
No, because it's the exact same x. It's mapping from itself to itself. The same way that when you're used to doing f of x is equal to x, it's mapping from the real numbers to the real numbers.
How do you... Wow.
So I'll let u be open in x, comma. Then, what is the preimage of u? Oops, let's get out preimage. What is the preimage of u equal to?
U.
It's just equal to u. Because the function just maps everything to itself. What does it map u to? U. Maps everything to itself. All the points that set u, it maps them right back to themselves.
Okay.
I don't know. 3. Therefore, maybe I should have said, then the preimage of that is equal to u, which is open. 3. Therefore, the identity function is continuous.
Right.
We showed that the preimage of any open set is open. Pick any open set out of x, run it backwards through the identity function, and you got another open set in x. Nice simple example. Okay, let's do a slightly more complex one. This time, let's prove that if f is a function from x to y, x and y have topologies. If f is a function from x to y, is a function from x to y, by f of x maps everything to y sub 0 for some y sub 0 in big Y. So pick some random point out big Y, doesn't matter which point. F maps everything to that one point. Or in other words, this is a constant function. You're used to working with these. It would be like f of x is equal to 5. That's a constant function. It maps everything to that one number. We're mapping everything in x to this one value in y. Which value doesn't matter, some value. Just like I could have said f of x is equal to a over here, where a is just some number. Some constant. So why not? It's just acting as constant. Maybe it would have been better to just call this like a little b. We usually use letters like that for constant, so maybe that keeps it more intuitive. So let's prove that constant functions are in fact continuous. And this works for any constant function. So this automatically works for all the constant functions you work with in your algebra courses. Okay, so 1. Let y, oh, we switched it to b. Let b be any point in big Y, comma, and let f be some function from x to y, where x and y are topological spaces, by f of little x is always equal to just that b. Okay, what do we need to prove?
That the preimage of b is open.
That the preimage of any open set in Y is open. So now I'm going to pick some random open set in Y. 2.
Oh.
Let V be any
Right.
open set in Y. I need to prove that its preimage is open in X. Okay, 3. Notice that V is open in Y, so V is a subset of Y. So then, either B is in V, or B is not in V. Has to be one of those two cases. That random B that we chose out of Y is either in the open set in Y, or it's not in the open set in Y. Has to be one of those two cases. For if B is in V, comma, then what is our pre-image of V?
X.
All of X. We mapped all of X to little b.
Yep.
And little b is one of the things in V. So therefore, the pre-image of V has to be all of X. Let's give a concrete example over here of a constant function. So here I'm at a to 1, b to 1, c to 1, d to 1. If I pick an open set over here that contains one, namely 1, 2, and I look at its pre-image using this function, so the pre-image of that, well, everything mapped to 1. So that's going to be the entire set X. Even though nothing mapped to 2, who cares? You had 1 in there and everything mapped to 1. So if B is in V, and my whole function maps to B, then the pre-image of V has to be all of X. Over-explaining?
Well,
5. If B is not in V, then the pre-image of V is equal to X is open. Maybe note that. X is open in X, right?
yeah.
Okay. Now if B is not in V, then the pre-image of V is equal to what?
X set.
The empty set, which is open.
Yep.
Everything maps to little b. If little b wasn't in our open set, then the pre-image of our open set is nothing. And so we just barely showed, in either case, our pre-image is open. So 6, therefore, f is continuous. Because we showed that the pre-image of every open set is open. Give me any open set you want, its pre-image is open. Because its pre-image is that or it's that. Those are both open. Cool. Subspace. Scary, scary. Going back to subspaces. Okay. So let y be a subspace of X, and let I be the function from y to X, given by I of y is just equal to y. So it maps everything in big Y to itself. We call it the inclusion function rather than the identity function. So let's get a picture of this. So remember that y is a subspace of X. So here's X, y is right here. Now we're mapping from y to X. So I just pulled out and read your y over here. So our function is mapping from y to X. But y is a subspace of X. Okay. So little y here gets mapped to this point. Here's I of little y. This point, it gets mapped to this point. What gets mapped to this point? Which points got mapped to here?
Nothing.
None. So the pre-image of that is the empty set. Okay. So if we pick some random open set over in X, pick some random open set in X, like U. Here's a random open set in X. Look at its pre-image. Here's the pre-image of U.
It's just the open set intersect y.
And it's just U intersect Y. Perfect. So the pre-image of U is just U intersect Y. That's what we meant by open sets over here in Y.
Yep. Okay.
So the pre-image is just U intersect Y. This is what we mean by open sets in the subspace topology. So this thing is an open set in the subspace topology. So the pre-image of U is an open set. We took an open set from X's topology, U, took its pre-image, and showed that it's an open set in Y's topology. Remember, what does it mean to be open in the subspace topology? You're written as an open set in X's topology, intersect Y.
Right.
So it's clicking in your heads perfectly that that's the exact definition of an open set over here. And so obviously. So we just took all those points, just kept the ones that were in Y, because it just maps the points in Y to the points in Y. Those are all the ones that get mapped. So intersect that with Y, that's exactly what needs to be open. Notice that our random open set over here could have also not had any overlap with Y. It could have been like V there. Well, what's the preimage of V?
The empty set.
Well, that's going to be V intersect Y.
Which
But
is,
since V and Y have nothing in common, it's just the empty set.
oh, I have a quick question.
Go ahead.
So if the pre-images of these empty sets, when they're not, or of the open sets, when the pre-images of the open sets are the empty set, my intuition is telling me that when we run the empty set through the function, first way around, do we get those sets back? Like, so we have the sets over here. The pre-image of those sets is the empty set, but when we
That
get
would
the
only
set-
be the case if you have a bijection.
Why?
Because a bijection keeps one-to-one.
So there's no lost information.
Yeah, kind of. You can't go back and forth in general between a function and not lose things.
Oh, I see. But that is true in a bijection.
It is true in a bijection. You can go back and forth. So bijections, if you ever have a function, or if you ever have a structure-preserving function, it's always going to be a bijection. It might be a bijection that has some more structure on top of that, but it's always and forever a bijection. So our simplest structure-preserving function is just a regular bijection. And that is structure-preserving from one set to another set. The only structure a set by itself has is the size of the set.
Right.
And so if two sets have the same size, if I can create a bijection from one set to another set, that means they have the same size, then they have the same set structure. And so we call them isomorphic. They're somehow the same. And so a bijection is a set theoretical isomorphism.
Yeah.
We're interested in more than just set structure, we're also interested in topological structure, so we're interested in homeomorphisms, which will be a type of bijection. But yes, good intuition there. So yeah, it's not going to be the case you're thinking, the preimage of V, well that's the empty set, so run the empty set through the function and we should get V.
U intersect Y doesn't do that either. You lose information.
Yeah, same thing here. The preimage of all of that, run it backwards, now run it through the function again, now we only got that portion
I'm
of
not
it.
gonna get the whole U.
Yeah.
Right, okay. That makes total sense, man.
Okay, perfect. Because bijection can go back and forth all day, everything plays nice. Okay, did we finish proving that or did we just talk about it?
Talk about it.
I guess we could quickly prove it just saying it. I don't think we need to write anything. Let U be any open set in X. Then the preimage of U is just U intersect Y. U intersect Y by definition is open in Y. We're done.
Awesome.
And it could be that looks like that, or it could be that gives you the empty set. Who cares? Open in Y, open in Y. And that's exactly what we would write out as a proof. Okay. Think we're good. We talked about that. Talked about the picture. I think I want to do example. Talk about it, do example, come back. I think that's how I want to do this. Okay. So now, you probably noticed as we were checking if each of these were continuous, that's a little bit tedious to have to check every single open set and see if its preimage is also an open set. That's obnoxious. Could we just check the basis elements? And if the preimage of every basis element is an open set, then it's continuous? And the answer turns out to be yes. So that's what we're going to prove here. So let X be a topological space, let Y be a topological space, and let beta be a basis on Y. Then F from X to Y is continuous, if and only if, for every basis element, its preimage is open in X. So if we take all our basis elements, look at their preimage, and it's still open in X, our function is continuous. So I don't need to take every open set in Y and look at its preimage to see if the function is continuous. I can just take all the basis elements in Y and check their preimage. Now, does that really help us? Because we still have to check infinitely many basis elements. And the answer is yes, it helps a lot. And we'll give some examples of how it helps a lot.
Can you remind me what a basis element is?
So, the one that we often use is, what is our basis for the sharing topology? Open intervals.
Just any open intervals?
Any open interval is a basis element on a sharing topology. Our open sets are anything we can construct from our basis elements.
Wouldn't they be the same thing though?
No. A basis element is always an open set. An open set is not necessarily a basis element. this 1, 2, union together with 3, 4, this is an open set in the standard topology.
Yes.
It is not a basis element.
So what?
Here's a basis element. Here's a basis element. Our basis elements are open intervals.
Gotcha.
The intuition I tried to give when I first introduced them is, think about basis elements as being individual Lego pieces, and then our open sets are any possible Lego structure you can build.
Yes. Okay.
And so every individual Lego piece is itself a Lego structure, but any union of them is also a Lego structure.
Gotcha. Okay. Thank you.
Okay, so say what this theorem is one more time, make sure we're all on the same page. I've got a topology on x and topology on y, and I've got a function from x to y, and I'm wondering, is it continuous? The way we would normally check it's continuous is we would say, take all your open sets from here, run them backwards through the function, and make sure they're still open here. What we're going to prove is, actually, you can just take all the basis elements here, run them backwards through the function, and they're still open. And if the preimage of all the basis elements is open, then the preimage of all the open sets is going to be open. And so we're good. And so we'll prove that's a logically equivalent definition. Proving that a function is continuous if and only if the preimage of open sets is open is logically equivalent to a function is continuous if and only if the preimage of basis elements are open. So we can reduce it to the basis elements. That's what this is. So let's do an example doing that, see how this is so useful, and how we can start instantly proving tons of functions are continuous that you know and love, and then we'll go back and actually prove it. Okay, so we're going to work with 3 functions at a time. F of x is going to be x plus 2, g of x is going to be 2x minus 1, h of x is going to be x squared. First thing I want us to get a little bit comfortable doing before we do this is just calculating the image and then the preimage of these things. So here's f. I want to know the image of the interval -1 to 2. So here's f of x. It's x plus 2. I'm running through that function all the numbers from -1 to 2. So I'm plugging in -1, I'm plugging in 1/2, I'm plugging in 0, I'm plugging in 1, I'm plugging in 5/9. I've run all the numbers from -1 to 2 into that function. What are all the numbers that come out?
Interval 1 to 3, not including 1 or 3.
1 to 4, right?
4, sorry.
All the numbers from 1 to 4 is the interval that comes out.
Yes.
If I run -1 through there, 1 comes out. If I run 2 through there, 4 comes out.
Yes.
And then any number in between those two is going to spell a number in between those two.
Yes.
Okay. Now, what is the preimage then of f? What's the preimage of the interval 1 through 4 on f?
6.
What's that?
3,6.
The preimage.
Oh, preimage.
It's -1, 2.
-1 to 2.
Yep, makes sense.
So in that case, they happen to be the same things. The image of that happened to be the same thing as the preimage.
You're saying happen to be. I mean,
Well, notice over here, it wasn't necessarily the case.
right. Yep.
So running the domain through gave us an image, and the preimage gave us the exact same thing we ran the domain through. We could then plug it back in. So this function happens to be a bijection. Okay. Looking over here at G. What is the image of -1 to 2?
-3. Common. -3.
-3 to 3?
Unless I'm blanking.
When we run -1 in there, 2 times -1 is -2, minus 1 is -3, good. Then we run 2 through there,
It's 4 minus 1, which is 3.
4 minus 1, which is 3.
Yep.
Notice that this spanned, from -1 to 2, spanned a distance of 3. This one's doubling whatever we do, so this better span 6 units. So intuitively, I look at that, my intuition instantly says, no, that seems right. Okay, let's try it for H here. Oh, let's do preimage. Preimage now of 4 to 7. Sorry, let me do 4 to 8, keep it. Let me pick odd numbers. Should have thought more about this.
Oh.
We'll do 3 to, how far should we go? 11?
One is rounded.
That's still a pain.
So we're wondering, what x gives us 3? What x comes out 3? So you're just working backwards. So you add 1, divide by 2.
It's 2.
Then
It's 2. It's 2.
11.
And then 11. So we're wondering what x comes out 11.
2 and 6.
Minus 1 divided by 2. Right?
Plus 1.
There we go. No throwing you off, is there? Okay. Now let's try it for h. What's the image of h? If we plug in the numbers from 1 to 2.
1. Oh, that's 1, 2.
Or sorry, negative 1 to 2.
It's 1 to 4.
1 to 4?
Yes. The interval 1 to 4.
This one we need to drop out. I'll tell you your answer's wrong. And then you can start pondering why. We are looking at the image from negative 1. So negative 1 is going to be somewhere like right there. Negative 2, 1, no. So I have it drawn, 1 has to come further up. Not very much to scale, sorry.
Oh, it could be both.
So if we're looking at the pre-image from negative, or the image from negative 1 to 2, that's all the points from here to here. And this hopefully goes up to about 4. So 1, 2, 3, 4, right? So we map out to all the values from here. We get this value, we get all the way down here, and then back up again. And so these are all the outputs we get. Right? Because this point maps right here, this point maps to 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 here. Come around the other side, this point maps to here, dot, 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 dot. And then finally, this point maps to here. That point maps to there, right?
Yeah.
So what are all the values that come out?
0, 4.
0 to 4, including 0.
Weird.
So this was
Yeah,
0 to
that
4,
makes sense.
like that.
Super confused.
Let's say this again. Let me try and draw a slightly better picture. So we're doing a quadratic. Just grab one. 1, 2, 3, 4, 5. That should be plenty. 1, 2, 3, 4, 5. Coming up. 1, 2, 3, 4, 5, 6, 7, 8. Try and get at least 9. Okay, so our function is x squared. So 0 goes to 0. 1 goes to 1. 2 goes to 4. And 3 goes to 9. Similarly, negative 1 goes to 1. Negative 2 squared is 4. We can try and line those up half decent. And negative 3 goes up to 9. Okay. Still not going to get a perfect picture, but much better than what I had before. Okay, so we are looking at the pre-image, or we're looking at the image from negative 1 to 2. So I'm taking all the points from negative 1 over here to 2, and I'm looking at what all the outputs are that I get if I map those points. So I get all the values that the function takes on in between there. All the height of the function, whatever the height of the function is at each point in between.
Oh, that's so weird.
So at negative 1, we map up here. So do one of our standard t-charts. Here's all our x values. Here's our f of x values. So we see that negative 1 would go to 1. We see that 0 would go to 0. We see that 1 would go to 1. We see that 2 would go to 4.
Okay, it now makes sense. I got it.
All right. And so we would get all the numbers from 0 to 4 to spit out of this thing if we plugged in all the numbers between negative 1 and 2.
Right, okay. Yeah, that makes more sense.
Okay. Now, sometimes you just need to see an obvious picture. It's confusing until it's obvious, and you're like, oh, duh. Okay. Now the tricky part. Let's look at the pre-image from 1 to 4.
Okay, so
0.
1.
The pre-image of 1 to 4. So in other words, maybe a picture here would help a lot. I assume it would. So try and redraw that in. Put that line back, put this line back. Okay, so now we're looking at the pre-image from 1 to 4. So we're saying what are all the x values that gave this as an output? From 1 up to 1, 2, 3, 4.
Well,
What are all the x values that spat out y's in this range? What are all the x values that when you run it through the function, you get a number that comes up in the orange here?
it's negative 2 to 2. Add 2 to 2.
Negative 2 to 2?
Yep.
So you're saying negative 2 to 2. Let me pick a random number in there.
Okay.
I'm going to pick 1/2. That's in there, right?
Uh,
What's 1/2 squared?
1/4.
1/4.
Oops. Yeah.
When I plug in 1/4 in here, in the orange?
No.
No. So that can't be the pre-image of 1 to 4.
Is it? Wait, what? Is it positive or negative 0 to 2?
Positive or negative 0?
Okay, so okay. A negative number squared would be a positive number, so there has to be there has to be two inputs for that image, right?
Okay.
I'm not really sure how to say that.
Oh, it could be a negative, that's true.
But
Do we include that?
the pre-image
Yes.
has to be a
I
positive.
want to know all the points that I can plug into this function such that their output is one of those orange numbers.
Yes. So would it be a union of open intervals?
Yeah, you're definitely going to get a union of open intervals.
Is that the best way to write that?
I don't know another way.
Oh, okay, so.
Oh, sorry, I drew my orange up too high here. Should have stopped here. Right, it was 1 to 4.
Yes.
Sorry about that.
So it's just go straight over, theoretically, that's, so it'd just be
Oh, wait.
negative 2 to 2.
No, I said that, it's wrong.
That was the first thing you said.
Oh, I apologize, I'm just catching up now.
That point should have been marked better. This point was 2, 4.
Could you do it too simple?
Yeah.
What is it?
No, oh, okay, wait.
So it's.
So we want all the points that map to here on this side,
So
and
negative
all
2
the points that map to here on this side.
So it's the,
Union of negative 2 to 1.
Yes.
Negative 2 to negative 1, union together with 1 to 2.
and 2, yeah.
Okay, there we go.
Okay, we got there again.
We got there in the end. So this is equal to negative 2 to negative 1, union together with 1 to 2.
That is cumbersome.
All right. Well, still not bad.
Makes sense. So
Okay. Now let's do this in general. So now I'm going to give you some arbitrary interval, a to b, and I want you to tell me its pre-image.
Okay.
So now we're back to f.
Yep.
So if a came out, what do I have to plug in? If a is what came out of x plus 2, what did x have to be? If I have to add 2 to x to get a, then what is x?
A minus 2.
A minus 2.
Okay.
Let's subtract 2 from both sides, right? Okay. So for the a, we got minus 2 there. And a goes to a minus 2, and b goes to b minus 2. When we take the pre-image. So when we took the pre-image of 1, we just minus 2 from it, which got us negative 1. When we took the pre-image of 4, we just minus 2 from it, which gave us 2.
Right.
So that's the interval. Now notice what we just did. Notice that a to b, this is a generic open interval on R. And we showed that its pre-image is some open interval, which is an open set.
So it's continuous.
So this line right there is enough to prove that this function is continuous. Because the pre-image of any open interval is still just open interval. So I showed that any of its basis elements, any basis element you choose, it can be represented as a to b. Take its pre-image, we got an open set. If the pre-image of every basis element is an open set, the function is continuous. That's why this theorem is so useful. The point of all these examples is to help you see why this theorem is so useful before we prove it.
Okay.
So yeah, it makes it that easy to prove that function is continuous. Let's look at the next one. G is a function to 2x minus 1. I'm going to run through I'm looking for the pre-image of the interval a to b using G. How do we find that? It's the exact same thing.
A plus 1 divided by 2.
Exactly. Plus 1 divided by 2. So a plus 1 to both sides and divide by 2. So x is going to be equal to a plus 1 divided by 2. That's what we plug in for x to make a come out. And similarly, if we plug this in for x, we'll get b to come out. So our preimage is going to be all the numbers from a plus 1 divided by 2 to b plus 1 divided by 2. And notice that's exactly what we did in our preimage here. Take the preimage of 3, add 1 divided by 2. Take the preimage of 11, add 1 divided by 2. So that function is continuous. Okay, now let's talk about the square root function. We're going to talk about h inverse of a to b. And we're going to break it up into 3 cases. So write out our first case here. So if my interval is like this, remember by definition b is the bigger of the 2 numbers, a is always the smaller of the 2 numbers. So b is up here, and then a is right here. So the first case I'm going to handle is where if a is greater than or equal to 0, so if my whole interval is greater than or equal to 0, then what is our preimage? This number right here then is a number such that the negative version of the number such that when you square it you get b. So this is negative the square root of b. So this number right here, that one right there is negative the square root of b. And when you square it, you get exactly b. This number right here is just going to be negative the square root of a. This number right here is just going to be the square root of a, not negative. And this number right here is just going to be negative, or is just going to be the square root of b. And that's exactly what we got. So we were looking at the preimage from 1 to 4. So it's going to be negative the square root of b to negative the square root of a, union together with the square root of a to the square root of b. So if I would have asked you for the preimage of 2 to 11 now, gave you not such pretty numbers, it would have been the interval negative the square root of 11, comma, to negative the square root of 2, union together with square root of 2 to square root of 11, whatever those numbers are. Those are the numbers such that when you plug it in to the squared function, you would get the numbers from 2 to 11.
Makes sense.
Okay, now we're going to handle the case where a is less than 0, but b is still greater than or equal to 0. So it straddles the real number line. So then, probably easier to just draw out the whole picture and read it. So this time, we have b is somewhere up here, and a is somewhere down here. So here's the interval we're talking about. Now, what are all the numbers? So if this has a height of b, all the numbers that are going to map to this height, notice that we can't map down here, right? So all the numbers that will fit within this interval are going to be all the numbers that gave me a height here, all the way over to whatever gave me the height here. And that's going to be negative square root of b to square root of b. And so in that case, negative square root of b to square root of b. Now notice if b was also less than 0, then it's just the empty set. Because I can't square a function and get a number less than 0. So if my whole interval is negative, I can't square a real number and get a negative number. A positive times a positive is positive, a negative times a negative is positive, 0 times 0 is positive. All right, we handled all cases.
So is this assuming that our function here is dealing with only real numbers?
Yeah, right now, each of these functions were from the real numbers to the real numbers. Sorry, I didn't say that.
Because you could map with the imaginary numbers, right?
We could talk about complex functions, but we're not going to.
Right, I'm not asking you to, I'm just wondering.
Yes.
Okay, yeah, that makes sense.
So, here's our preimage of our function. We gave it an arbitrary basis element in R, and we looked at its preimage. Its preimage either looks like this, or this, or this. Notice that this is a union of open intervals. That's an open set. That is an open interval. That's an open set. That's an empty set. That's an open set. In either case, the preimage of that interval was an open set. So the squared function is a continuous function.
Okay.
Okay, so with all those examples out of the way, let's now do the actual proof. Notice that this is an if and only a function. So I need to show that if this is the case, and this is the case, and then if this is the case, this is the case. So I'm going to go the forward direction first. So 1, let f be continuous. What am I trying to show? I'm trying to show that if f is continuous, then for any basis element you choose in Y, its preimage is an open set in X. So let f be continuous, and let B be any basis element. My job is to show that the preimage of B is an open set in X. 2. Since B is open in Y, then the preimage of B is open in X. Remember, your basis elements are always open sets. Right? So a basis element is always an open set. Our basis was a basis on Y. So it's an open set in Y. B is an open set in Y. And I know f is continuous. What does it mean for f to be continuous?
Its preimage is open.
The preimage of open sets is open. So that's an open set. That's its preimage. So its preimage has to be open in X. So what did I just show? I showed give me any random basis element you want. If our function is continuous, its preimage is open in X. Now I need to do the other direction. I need to show you that if for any basis element you give me, its preimage is open in X, then that function must be continuous. So now we're going the other direction. So this time, assume that for all B in beta, the preimage of B is in tau sub x. Let's assume that the preimage of every basis element is open. My job is to show f is then a continuous function. How do I show f is a continuous function, always and forever? Pick an open set, show its preimage is open. So now I need to grab some random open set. Some random open set out of where?
The image.
Which one? Tell me what set my open set comes from.
Tau sub y.
Tau sub y. So I need to pick some random thing in tau sub y. So let V in tau sub y. Grab some random set that's open in Y. My job is to show its preimage is open in X. Now let V in tau sub y. Since beta is a basis on Y, what do I know about V?
It's an open set.
I know V is an open set, but now, since I know that beta is a basis, what do I know about V? Look, if I told you
It's a union of basis elements.
it's a union of basis elements, perfect. Right? There has to exist some basis element such that their union gives me V. Remember, our topology was Lego structures. And I told you V is a Lego structure. What do you know? It's a union of Legos. So then there must exist some collection of basis elements, I'll call it B sub alpha, some random collection of basis elements, maybe infinite, maybe just one, I don't know, such that the union of all those basis elements is equal to V. Now, what else do I know about each of those basis elements?
They're open.
I know that they're open, but by assumption, what do I know about those basis elements?
They're in the topology. Well, yeah.
I know that their preimage is open in X. That's what we assumed. Assume that for every basis element, its preimage is open in X. So I know that V is equal to a union of those basis elements. So 5, then what is the preimage of B? So then, yeah, you seeing it?
Yeah, yes.
So then the preimage of B, well, that's the same thing as the preimage of
The union of the base.
B.
Yeah.
And now, going back to what I told you, we were going to have to use the preimage of a union is the same thing as a union of the preimage. So you can always pull a union out of a preimage. So this is equal to the same thing as if we unioned up all the preimages we would get for each of those basis elements. Okay? Now, we have a union of the preimage of basis elements, but the preimage of basis elements is open in X. So we have a union of things that are open in X. And a union of open sets in X is an open set in X.
Yes.
Any union of open sets is an open set. So this, which is open in X. Set 6. Therefore, F is continuous. We've already showed pick any random open set you want. Its preimage is open. So the function is continuous.
Okay.
Super abstract, but real easy to prove these
That makes
things.
sense, that makes sense. Quick question. So when you put the B there, did you mean to draw that little thing that comes underneath it? Is that
Oh, sorry. So that's a B sub alpha.
Uh-huh.
So we use sub alpha to mean that this set cannot necessarily be indexed.
What do you mean?
This goes back to countable versus uncountable. So an index set is a set that can be counted.
Okay.
So we're saying this can't necessarily be counted. It could be infinitely many of these things, and it could be the infinite that's an uncountable infinite.
Yep. So why don't you put the little thing underneath it? Well, okay.
So we use the sub alpha, and we put it in brackets right here, so it's a collection of things that can't be indexed.
Yes, but is that
Necessarily. Maybe they could, but we don't know that they could. Another way you can think about that is that it's often read as an arbitrary collection of whatever that thing is, basis elements. That's often how it's also read.
okay? Yeah, I figured it out. Right.
Okay. So, yeah, that's how we represent it. It's a collection of things, and I almost know nothing about this collection. Could be infinite, like the real numbers are infinite. Could be countable. Could be 1. Could be empty. We almost know nothing about it. It's completely arbitrary. All we know is that they're all basis elements.
Okay.
Okay. Yeah, I'll try and make my alphas not look like x's, because I know it's real sloppy. Those should all be just write one big. I'm trying to make it look like this. B sub alpha.
And that's a B, not a beta.
That's a B, not a beta. I tried to do my beta like that. So try and put a
Yeah, that was what I was confused
thing
about.
on the bottom
Right. Because
to help make it clear. And make sure I don't have a straight line at the top. Yeah, a lot of just getting used to handwriting.
Yeah, no, that makes sense. Gotcha.
So beta is always a collection of basis elements, and B's are always the individual basis elements. A lot easier to tell when you're reading a book versus looking at handwriting. Any other questions? Okay, let's move the camera. Whew. It's already 8:38.
Do you know if the building is unlocked?
I have no idea, but I highly doubt it since it's break.
Should be fine.
Jeez. Feels far. Okay. Don't know why I'm looking at just gonna grab the orange. Kids have to scribble on pictures. Okay, so let's prove a couple more functions are continuous. The next function that we're going to prove is continuous is we're going to look at f from, it's going to be a function from r squared to r. What are the inputs going to be? Ordered pairs of numbers. And it's going to spit out one real number. You're going to give it two real numbers, and it's going to spit out one real number.
Didn't even know you do that. Okay.
Yeah, multivariable function. And it's just going to be a very simple function. It takes x and y and spits out their sum.
Okay.
So you give it 1 and 3, it spits out 4.
Mm-hmm.
Really simple function. Takes two numbers, spits out one number. Okay. I'm going to show that this thing's continuous. How am I going to do that? Exactly using our previous theorem. I'm going to pick some basis element in here. Understood that we're talking about the standard topology on each. So what's the standard topology on R? Open intervals and unions of open intervals. What's the standard topology on R squared?
Open balls.
Open balls and unions of open balls. Just real quick sanity test. If we're in R2, is this an open set? Yeah. Could create a bunch of little open balls, give them as fine-tuned as small as I want to perfectly get that border. Because I can make them arbitrarily small and get arbitrary precision there. Good. So, we are mapping from open balls, we're mapping from R2 to R. And so, intuitively, we're going to have to, what this function is going to do is it's going to map entire lines to single point. Entire line to single point, over and over again. You'll get intuition for it here in a second. Sounds hard, but then you'll see it and you're like, oh, duh.
Alright.
So, and how are we going to prove that this function is continuous?
With our basis elements.
We're going to pick a random basis element in here, look at its preimage, and see that its preimage is an open set.
Okay.
Now, we're not going to do full proof, we're just going to see it pictorially. And I think that'll be enough. Okay, so first of all, it's the same thing we did over there. When does this function spit out A? I want to know, when does x plus y spit out A? And notice that x plus y equals A is the same thing as y equals negative x plus A. And you are very used to seeing functions that look just like that.
Yep.
And it's in what your favorite form,
Yep.
the slope-intercept form. You know that A is where it crosses the x-axis. And you know that the slope of this line is -1. Now, for the sake of pictures, let's pretend that A happened to be a negative number and B happened to be positive. They could have both been positive, they could have both been negative. All we know is B is bigger than A. I'm drawing it out so that A is going to be negative, B is going to be positive. Okay, but anyways, so here's the line, y equals negative x plus A.
Okay.
This is the line that gets mapped to A under our function. Pick any point on that line, and it spits out A.
Okay. Yeah, that makes sense. Yeah.
Yeah, I told you, once you see it, it's kind of obvious. But it's kind of cool when you stop thinking about it as a picture and think about it as mapping from one space to another space.
That's so.
And so we map that whole line all to the single point A.
Do they all map onto their y-intercept?
In this case, they're all going to. So we're just mapping, but we're mapping lines with the slope of -1 to their y-intercept. That's essentially what we're doing. So we're mapping a whole plane onto a line.
Yep. Okay.
Okay. And similarly for B, assuming B is some positive number. If we're looking for where x plus y is equal to B, that's the same thing as y is equal to negative x plus B, which is a line that with B as its y-intercept, slope -1. So, redrawing our picture now, here's where A mapped to, here's where B mapped to. Any point between A and B would have just been a point whose y-intercept was between here. And so the pre-image of AB under this function is what I have colored in here. It's that strip. It's all the lines with the slope of -1 whose y-axis is between A and B.
Yep. Okay. Yep. Makes sense. How do you write that actually? That strip. How do you write that strip in terms of intervals?
Oh, you just write it's the points greater than this line and less than this line.
Okay.
You've probably done it a couple times.
Yeah.
So it would be, if you want me to write this out exactly, it would be all the points where y is greater than negative x plus A and y is less than negative x plus B. And those are the exact points. Anyways, so there we go. There's the image of the addition function.
Preimage.
Or the preimage of the addition function.
Yeah.
So notice it maps that whole strip to that open interval.
That's cool.
Preimage of open sets, open sets. Okay, now we're going to prove that multiplication is continuous. Similar thinking here. So multiplication is a function that takes two numbers and spits out a number. We're going to take x and y, and we're going to spit out x times y. And now, you probably don't have very much experience working with hyperbolas, but each of these is just a hyperbola. X times y equals b, that's going to be a hyperbola. X times y equals a, that's going to be a hyperbola. If a is a smaller number than b, in this case, a and b both have to be positive numbers, right? I can't get, I guess I can. You can get the negative and the positive. Never mind. Should have said that. Because it just changes the signs on these when a is negative or when it's positive. Okay. But all the numbers x times y that equal a, that's this dotted line and this dotted line. All the ones where it's equal to b, that's this dotted line and this dotted line. Comes up on both sides.
Okay.
And so any points in between would be those open strips. And as weirdly shaped as those open strips are, they're open strips.
So we're not mapping it onto a line anymore?
It doesn't map onto a line. This time it maps onto a hyperbola. Addition, the preimage of a point under addition happened to be a line. The preimage of a point under multiplication happens to be a hyperbola. We can do this really concretely. Think about it in the case of 2. So I want where x times y, well, maybe equals 1, is an easier way to think about it. So just to get you some intuition for the scene. If x is 1, actually, maybe I want more space to talk about some fractions. So 1, 2, 1, 2, 1, 2, oops, minus. We don't need a label, we can tell. Just make a mess. Okay, so let's look at this function. If x is 1, y has to be 1. If x is negative 1, y has to be negative 1. If x is 2, y has to be 1/2.
Right.
If x is 1/2, y has to be 2. And if x were 100, y would have to be 1/100th.
Okay.
Yeah, okay.
And if x were negative 2, y would have to be negative 1/2.
Yeah, alright.
And so you get the shape that I was trying to draw over here.
Okay, that makes more sense.
And then if our number happened to be negative, then it flips.
Great. Gotcha.
Yours. Okay, so we just really showed that addition is continuous, and we showed that multiplication is continuous. We're not going to bother proving this next one, but try and give you intuition for it now, which is any polynomial is continuous. You know what a polynomial is?
Yeah.
What are the restrictions on it? So a polynomial, so every polynomial function, so p is from the real numbers to the real numbers by p of x equals some real number plus some real number times x plus some real number times x squared plus ... plus some real number times x to the n. If it can be expressed that way, it's a polynomial. So, quick sanity check. Square root of 2 plus 10 times x to the 3. Is that a polynomial?
Yes.
Yes. Because it can be expressed as some number, that's our a sub 0, plus some number times x, plus some number times x squared, plus some number times x cubed, up to some n.
Gotcha. Yep.
So that's a polynomial. Let's try one more. X to the 1/2 plus 2x. Is that a polynomial?
Yeah.
The answer is no. All our x's have to be natural number exponents.
Why though?
It's just a definition of what makes a polynomial.
Okay.
So it's just a by definition thing.
Yeah.
Let's try one more. 2x plus 4x plus 6x. Is this a polynomial? Read the definition carefully.
No.
If it can be expressed this way, it is. Can that be expressed this way?
No.
No, there's no way to do it. Unless, of course, we express it as 12x, and then yes, obviously.
Yeah, right.
So this is 12x. They are identical. They are one and the same.
But 12x is a polynomial. And
And 12x can be expressed this way.
Right, but that's I can't.
Sure it can. Because this is this. There is no difference between them.
So is it a polynomial?
It's just like if I had written out the words 12x. That's no different than this thing.
So it is a polynomial.
So it is a polynomial.
Wow.
Because it is this. And this is a polynomial.
Right.
Sometimes we get a little confused about what identity means. They are one and exactly the same. There is no difference between them.
So they share the same properties.
So they share identical properties. The same way that you share identical properties with you. You are you.
Right.
And everything that's true about you is true about you. Everything that's true about this is true about this. That's what identity means. Sometimes we think a little too softly about identity. Very strong word. Okay, so intuition for polynomials. Now we're not going to prove that polynomials are continuous, but notice that what do polynomials do? They just multiply terms together and add terms together. So we already showed multiplication is continuous, and we already showed addition is continuous. And so just doing that operation over and over again, hopefully it appeals to your intuition that it's continuous. We can prove it is continuous, but that requires using some summation notation, which I'm afraid would confuse you more, would help, and doing a proof by induction, which I'm also afraid to do. But these are the big ideas behind the proof. It's just using this and this over again. Okay. So now, our next proof here. Let f from x to y be continuous, and let a be a subset of x. Then x is in the closure of a, then if x is in the closure of a, then f of x is in the closure of f of a. Okay, let's remind ourselves of closure. What's the closure of a set, intuitively speaking?
The smallest closed set that contains a set.
The smallest closed set that contains a set. Or the intersection of every closed set that contains a set. Fantastic. So that's what closure is. Now, I told you, when we went over this theorem, 2.5, that you need to remember always and forever because it always sneaks its way back into the class. Always pops its head up. So, remind you of this theorem. This is one that we proved a while ago, but told you it's never going away. We proved that x is in the closure of A if and only if, for every neighborhood of x, it intersects A. So that neighborhood intersecting with A is not empty. Remember, if your intersection is not empty, that means you have something in common. So if every neighborhood of x has something in common with A, then x is in the closure of A. And then I also warned you that oftentimes we use this theorem in its contrapositive form. So that's where you negate both sides. If every time this is the case, then this is the case, and every time this is the case, then this is the case, is logically equivalent to then, if every time this isn't the case, this isn't the case, and if this isn't the case, this isn't the case. Oh, sorry. I meant to point to the same one twice. If every time this is true, then this is true, and vice versa, then every time this is false, this must be false. So this is saying the false version of this. This is a negation of that, this is a negation of that. That's what I was trying to say.
Gotcha.
Or it's just contrapositive if you remember contrapositive. What does this say? What does the back and forth arrow mean? It means alpha implies beta, and beta implies alpha.
Right.
The contrapositive version is contrapositive of alpha implies beta is not beta implies not alpha. And the contrapositive of beta implies alpha is not alpha implies not beta. I don't know why I paused. It's because I wrote negative there. Not beta. And so, rewriting this is the same thing as not alpha. I keep doing negative. Driving me nuts. Not alpha is logically equivalent to not beta. The same way that this is the same thing as alpha is logically equivalent to beta. So if you have alpha is logically equivalent to beta, you can negate both sides and it's still true. Okay. So we are going to be using this form of the theorem, the bottom one. But the top one is what we proved when we proved it, I think. I don't remember which one we proved, but they're logically equivalent. Okay, so I'm going to have to use this. Here's what I'm proving, but I'm going to actually prove the contrapositive of this. So we're supposed to show that if this is the case, then this is the case. I'm going to show that if this is not the case, then this is not the case.
Okay.
Which is saying the same thing, right?
Yes, yes.
Okay, contrapositive. All right, here's the picture for what we're going to do. So I'm going to start right here. I'm going to say 1, assume f of x. Well, we need to say what x is. So let little x be any point in big X such that f of x is not in the closure of A. So I'm starting out with where this is not the case, and I'm going to show that then x was not in the closure of A and we're done. So I'm going to show if its image was not in the closure of f of A, then it couldn't have been in the closure of A. That's what I'm going to show. Here's big picture how I'm going to show this. Here's big picture what we're doing. So I'm going to say if f of x is not in the closure of A. So here's the closure, here's our picture. Let's just talk about the picture for a second. Here's x, here's y. F is mapping from x to y. Here's the closure of A. When you map it under F, it gives you this thing. Something. We picked some random point x that for sure was not in the closure. Sorry. We picked some random point x such that for sure f of x was not in the closure of f of A.
Okay.
Our job is to show x is also not in the closure of A.
Okay.
So I'm trying to show that this is not in here. I know f of x is not in here. I'm trying to show x is not in here.
Oh, yeah.
Now you might think this is obvious. You might think, well, if x was in the closure of A, that obviously means that f of x is in the closure of f of A. Isn't that obviously the case? If f is in the closure of A, then f of x is in the closure of f of A?
It feels like it is.
It almost feels obvious. I know it almost feels obvious because I have to take 2 glances at this. That would be the case if we said f of the closure of A.
Right.
If x is in this, then obviously f of x is in that. But that's not what we're talking about.
Okay.
We're talking about f of A, then take the closure.
Right, that's big difference.
So this is not just the image of this thing.
Okay.
The closure of f of A is not the same thing as the image of f of the closure of A.
Yeah.
A lot easier to write than to say. This is not the same thing as f of A closure. Necessarily. Okay. So, at first it seemed like, oh, that's stupid simple, then realized, okay, there's a little bit of subtlety to it. That was a trap I almost fell into when I first read it. Okay, so here's what we're setting up. I picked x in big X, I picked little x in big X, such that its image for sure is not in the closure of A.
Okay.
Or in the closure of f of A. Alright, now, looking at this. If x is not in the closure of some set, then there must exist some neighborhood containing that point, such that that neighborhood does not intersect the set. So, since f of x is not in the closure of f of A, then I know that there must exist some neighborhood V containing f of x, such that V does not intersect f of A. It might intersect the closure of A, but it doesn't. It might intersect this set, but it doesn't intersect just f of A. Careful what this says. If x is not in the closure of A, then there exists some neighborhood such that that neighborhood doesn't intersect A. So I know too. Yeah, a little bit subtle there. So then there exists V in our topology on Y such that f of x is in V and V intersect f of A is equal to the empty set. Those 2 points have nothing in common.
Yeah.
Okay. We're trying to show that x is not in a complement. Sorry. Yes. I'm trying to show this not being the case implies this is not the case. Okay. So, 3. Let's talk about the preimage now of V. So that's the thing we have over here. I'll just call it U. So I'll let U equal the preimage of V. And observe that U intersected with A is equal to what?
So,
The empty set. How do you know? Because V has nothing in common with f of A. And so V's preimage, which is U, must have nothing in common with A. If they had a point in common, then when you run it through the map, there would be a point in common over here. If little a,
oh, it's continued, yeah.
if little a was in both these sets, then f of little a would be in both these sets.
Yep.
But I know the intersection of those sets is empty.
So they can't be true.
So the preimage of this and the preimage of this take their intersection. That has to also be empty.
Yep.
Perfect. So then U intersect A is the empty set, and also X is in U. How do I know X is in U? Because f of X was in V.
Yep.
So what did I do? I found some open set that contains X
That doesn't intersect.
that doesn't intersect A. So what do I know then? If I found some open set X that can, or sorry,
It's not in the closure of A.
it's not in the closure of A. Perfect. Not being in the closure of A is identical to if there exists some open set, some neighborhood of X, some open set containing X, such that when we intersect it with A, we get the empty set, then it's not in the closure of A. I just barely found some open set U, such that when you intersect it with A, you get the empty set, and it has X in there. So, then, or therefore, X is not in a closure. Perfect. So I showed if this is not the case, then this is not the case. Which is the same thing that if this is the case, then this is the case.
Right. Wow. Would it have been easier to prove it the first way without the dots?
It kind of depends on what you're going for here. What's nice about this way, when I think about it this way, is if I'm looking for a set, then I want this one. Because then I just need to find one.
Yes. Right.
Notice that this one's talking about for every, this is talking about can we find one.
Yes.
So it kind of depends on your context, which of those are easier.
I see. Okay.
But in our context, it was much easier to talk about finding a set that broke it.
Okay. Yeah, makes sense.
Or finding a set that worked out. Okay. Ah, shoot, we're already at 9. Wanted to tie it back in with what we started with.
I've got all night, so.
Let me just say it one more time, and then, because we still have a list of theorems here to prove. These are each theorems that each need written out and proved, so there's no way that we're going to get through those. But, so let's restate now the Epsilon-Delta definition of continuity that we had over there, but restate it now more topologically. So a function f from x to y is continuous if and only if for every open set V and Y, where f of x is a point in V, there exists some neighborhood of x in big X such that the image of that is a subset of V.
And X and Y are both topological spaces.
X and Y are both topological spaces. So this is converting the Epsilon-Delta definition over there into a more set theoretical one. I told you we're going to work it all the way to showing it's the same as our topological one. But notice what we were doing over there, just redraw over here since the camera's over here. What we were doing over there is we have some function. Your job was, if I give you some interval here, you had to find some interval here. Sorry, let's actually pick one that works. you had to find some interval here that mapped all its points inside of here. You didn't have to get a perfect mapping that got exactly the whole interval. Oh, pretend I did that better. So that maps to this interval, right? So that's what our epsilon delta definition was saying over there. So notice, in terms of that, here's our u sub x. Let me draw this one more time better, because that was just hideous. If I would stop and think for a second rather than just rushing, we could actually make it look good. Okay, so we've got some x here, runs through our function. Here's the f of x. What we need to show is that for any open set you pick containing f of x, what we were talking about for our epsilon delta definition over there, any open set containing it, so this right here is my v.
Okay.
This is v. We can find some neighborhood of x, here's my u sub x, such that when we map it over,
It's in V.
it's in v. So this piece right here, just this piece, that right there, is f of u sub x. It's what we get when we map the intervals, right?
Yes.
Maybe do that in orange. So this portion is what we get when we map this.
Yep.
Map that through, it comes out right there. So notice what this is saying. The function is continuous if for every open set v in y, where it contains f of x, it has to be an open set containing the point we care about, there exists some neighborhood of x such that when we map that neighborhood of x, it all was inside of v. We didn't get points that went outside of v. Notice in our discontinuous ones, we were able to get points outside of the interval.
Yep.
So this is just a straight conversion of that epsilon delta definition to a more topological version. We still need to prove that this in fact gives us continuity in the sense that we know and love.
What do you mean?
So remember our exact definition of continuity. A function is continuous if the preimage of open sets are open sets.
Oh, yeah.
So I need to still show that this is the same thing as the definition we
So
gave.
that just rewrote what the...
This is just restating that in more topologically friendly terms.
I mean, we need to prove that that is actually the definition of continuity.
We need to prove that this is still logically equivalent to the topological definition of continuity.
Yes. Okay.
Right.
Yep.
So that's what this next one is. F from x to y is continuous if and only if for every x in every open set v and y where f of x is in v, there exists a neighborhood u sub x in x such that the image of that is a subset of v. So that would have been our next proof.
Yeah.
Proving that this epsilon delta definition is in fact logically equivalent to the definition we gave for continuity. So I think that's probably where I'm going to pick it up next time. That'll be a good place to recap and say, remind us what continuity exactly is and recap the epsilon delta definition. Because that's a big definition that, as you continue in your studies, you're definitely going to come across it. You're going to have a huge advantage over kids because they're going to look at that and say, that's just gibberish.
Is that when you take a standard calculus class, do they give that definition to you?
Textbooks are running away from it.
Are they?
They're running away from the dense notation. And so they give you this really wordy thing. They actually write out the full sentence. A function is continuous if for every positive number epsilon, there exists some positive number delta such that, and they do it all wordy trying to hide the notation from you because they're trying not to scare the kids. The better textbooks just give it to you and force you to get comfortable with the notation. Because it's really hard, once you understand the notation, it's really hard to consume that big sentence. It's real easy for me to look at this thing and know exactly what that's telling me. I was a little bit lazy. I didn't say for all epsilon in positive rails, there exists delta in the positive rails. So a little lazy there, but if I would have added those two pieces, then that's precisely what it is.
It's a new language, practically.
Yeah, and it's a dense language that communicates a lot and it communicates precisely. And you know exactly what it means. And so more and more modern textbooks are running away from they're running away from quantifiers in general.
Which sucks, because then you go to Wikipedia and you can't understand anything that's being said.
It's awful. No one who's competent in the material would actually write that way because it's just confusing.
That's true.
It's just way harder to consume when someone completely writes it out. So you'll probably get it. I don't know. You'll recognize it when you see it. And either they'll give you some paragraph or they'll give you the big boy definition.
Are you gonna teach calculus in high school?
I don't know. I do when I have students who are interested in it.
Oh, I see.
And so hopefully I teach you guys, but
How about that?
who knows what the future will bring.
Yeah.
Well, I've done it with as few as 2 students before. So even if you two can just hang in there
I would do that.
for you younger guys.
Yeah.
Then, yeah, I'll have geometry with you guys next year. We can turn this off. We're not going over anything else. And geometry is a great continuation.